There we go. Great. So feel free to use the chat anytime if you have questions. I'll be checking in on that. And if there are questions, we can resolve them from there. Great. Before I do get started on today's class, are there any questions from last lecture? It doesn't look like anything immediately, so we'll go ahead and get started. Now, last time we started to talk about the process of verification and validation and what it means to release high quality software and when we can answer that question of when we're ready to release our software. So the goal today is to dive into quality in much more detail. This is a little bit of repetition from your software architecture class, some of the same quality concerns. But like I said before, we'll try and put this in a bit of a different perspective because now we're really focused on how we assure the quality of the final system rather than just its design and architecture. So today we're going to focus on 5 specific aspects of quality: dependability, availability, performance, scalability, and security, and talk about how we build that evidence base that the system is good enough to release and how we assess whether we have high quality in these different attributes. Now, as I said last time, we all want high quality software. We all agree that quality is very necessary. What we don't necessarily agree on is what quality means. So if I ask 10 of you what is high quality, you might say 10 different things. And why that is because when we talk about quality, we're not just talking about what the software does, we're also talking about how it goes about delivering its functionality. So of course we care about whether the right answer comes out, but we also might care about how fast it delivers that answer, or how secure it is in protecting the data that it used to calculate that answer. If we want to use the system, we obviously want it to be up and running at the time we want to use it, not just at times they're inconvenient. And as we add more users, we care about still being able to deliver high quality to each of those users, right? So all of those mean that software quality is a lot more complex than just, did it give me that right answer? And it's hard to measure quality. It's hard to assess quality in an objective rather than a subjective manner, especially because you need to look at all these different aspects. So quality attributes are our first method of how we think about quality, how we can break this down from a very nebulous, high-level subjective idea, high quality, versus, well, what does quality mean from different perspectives? So these desire different aspects of quality. And developers have to take some of these aspects and decide, all right, for my system, what is most important to deliver on? What do I really need for my stakeholders? Now, for this class, the most important of these, and really in general, the most important of these is dependability, the ability of the system to consistently offer the correct functionality. So the right answers, not crashing, even under unforeseen or unsafe conditions. Now, a few others that we're going to focus on specifically, there's a million of these things, but 4 others that we're going to talk about specifically in this class because they're some of the most important are availability, the ability of the system to recover from failures or to avoid failures altogether. This is part of dependability, but it's also a standalone attribute looking at, well, if something bad does happen, how do we recover from it? How do we avoid this problem in the first place? If we're designing with availability in mind, you might be looking at factors like redundancy in your system. So if one process goes down, there's a backup that can pick up for it. You always want to make it possible to replace components when there's trouble, right? The next is performance. So when an event occurs, the system should respond quickly. We don't want to wait hours to get an answer to our questions. Performance is our ability of the system to meet our timing or our throughput requirements. The third is scalability. So based on our available resources, how can we scale performance to best meet the needs of the users we have, given the resources that are available? So if more resources are available, we should be able to scale to higher and higher numbers of users. And if less are available, well, we should be able to try and deliver good quality to each person we have to the extent possible without some waiting much longer than others. Right? And then the last is security. Our ability to protect the information in the system and the services of the system from unauthorized access while still providing these services and this data to our authorized users. So to start, most important of these, and the one we'll spend much more time on, dependability, right? Last time we asked this question, when is the software ready to release? And that isn't such a simple question, and it's not got one simple right answer. But basically, the answer is that when we can provide some sort of evidence that the system can be relied on, that it's dependable. And when we want to establish dependability, it's sort of a meta attribute. It really encompasses four things that we can talk about with the system. We want to show some subset of these, that the system is correct, that it's reliable, that it's safe, and that it's robust. Now, we might not meet all four of these. Often we actually don't, but we're aiming for all four of these to the extent possible. So what do these mean? Well, the simplest of these in definition, but maybe not in its actual practice, is correctness, right? So a program is correct if it's always consistent with its requirements. When we write requirements for a system, we're laying out these promises. It will do these things. And when the system acts, well, either we're going to have a successful execution of the system that's in line with these requirements that match everything we stated, or something will go wrong. And if it doesn't match the requirements, if it crashes, well, there's a problem, of course. But even if it doesn't crash, if it's not consistent with the requirements, then we consider it incorrect, right? Now, correctness is an all or nothing affair. You can't be 30% correct or 50% correct. You're either correct or not, right? So that means that it's actually really difficult to say whether your system is correct or not. Do you know? Have you tried everything that you can do? Proving correctness and how hard it is to prove correctness depends on how complex your system is, and it depends on how complex and thorough your requirements are. So if I hand you a requirements document and it's just one sentence, as it says, software works. Oh, someone has their microphone on here. Right. So I'm just going to hit that and mute everyone. There we go. Okay. So if I hand you like a one-line requirement specification and it just says, "Hey, the thing works," well, then hey, your program's correct, right? You said it works, it works. But if I write, 100-page requirement document with thousands of different requirements, it's a lot harder to show the system is correct with regards to each and every one of those, and regard to every detail of each of those. So a program can easily be shown to be correct when you're talking about a weak specification. On the other hand, though, it's often impossible to prove with a remotely good detailed specification and a fairly complex system, because that would require showing every possible behavior of the system under every possible input condition. So correctness is something we aim for, we try and get close to, but it's rarely something that you provably achieve. It's more just the aspiration. Now, instead, what we often aim for is reliability. Reliability is a much more specific quality goal. It's a statistical approximation of correctness. Last time we talked about the empiricist versus the rationalist, right? So the empiricist, the one who does experiments, this is what they be aiming for, is reliability. They're going to observe the system for a while, over some sort of period of observation. And over that time, we try and figure out how correct was it over that period. So over a number of system executions, over a certain time interval, we watch the system, we use the system, and as we use it, we observe what happens when we look for violations of our requirements, right? So if we see issues, that's great. We go and fix them. And if we don't, well, at least we have this evidence base that at least when we tried it, it seemed to work. And that's much more realistic than trying to prove it's correct under every possible situation. Now, again, it really depends on how thorough your requirements are still to see how thoroughly you can check your system behavior. And it depends on how good and thorough your efforts are during that time period. If that time period is the execution of one test case, that's not very thorough, right? You're still probably some issues. But if you observe it for a week and during that time you run 10,000 requests against it, that's a lot more thorough and a lot more likely to show that the system is statistically correct. Yeah, so there's in the chat, someone asked this would correlate to doing empirical verification. Yeah, so testing in itself is an experiment, right? And that's one way of assessing reliability is performing these trials, poke the system many times and see what happens and compare that to your requirements. Now, the thing is that when we assess reliability, we need some sort of measurement and some sort of threshold. But the other thing you want to consider too is from the perspective of different kinds of users. So often you have what's called a usage profile, which is some kind of expected pattern of interaction for different types of users. So for the power user, these are the functions they're going to use, how often they're going to use them, what sort of sequences they use those functions in versus a brand new user might use different functions or use them less often or have different use cases. So you want a little bit of consideration of what your types of users are and how they're going to interact with the system. And that's because reliability depends on who is working with the system. Some of your users might never trigger a crash. Others might see crashes happening all the time. Uh, so you can't really establish one level of reliability for everyone. What you do is you tend to do this for certain types of users. You come up with 3, 4, 5 different groups of users, and for each of them, try and assess reliability for them based on their usage patterns. Now, these notions, correctness, reliability, they have a couple of weaknesses, or maybe not weaknesses, but realities about them. And the first is that whether something is correct and reliable, that depends on that requirement specification. It's only as strong as your requirements are. If you have an undetailed specification, a short specification, it's really easy to say a system is correct or reliable, and bad things might still happen. It's all relative. Now, if the specification is too strong, then we can't show correctness. We can only aim for reliability, and even then, it might be a little difficult to assess it in a lot of detail. And the other thing about this is that your typical specification makes no distinction between a minorly annoying failure of your system and something that's life-threatening or financially threatening. And not all software faults are equal in the effect they have when the system fails. So for some kinds of system, it's really important to consider how severe a fault is. So we have two more properties, safety and robustness. Those address both of these issues. Safety revolves around a more limited specification where we look at major hazards that we have to avoid. So situations that we know could occur and could lead to a dramatic failure of the system. We look specifically at correctness and reliability with regards to those situations. Robustness, on the other hand, revolves around the idea that there's hazards out there that we don't know about. Things might happen that we can't really plan for, we haven't thought of. So we put safeguards in place. We're not psychic, but we put safeguards in place to prevent the system from doing something dramatically wrong if it's thrown outside of the expected operating environment. So robustness looks at these safeguards in place to gracefully degrade service when problems do happen. So let's talk about those in a little more detail. So safety is our ability of the system to correctly handle these planned hazards. So when I say a hazard, I mean a known, defined, undesirable situation. And these are generally prioritized by the severity of the problem. So it's annoying if Microsoft Word crashes, right? But when it restarts, they'll make some attempt to recover your document and it might be fine. But if it corrupts your document, if there's no recovery, that's a much more difficult situation. If there's a brief graphical glitch on your heads-up display in your airplane, That's concerning, but probably nothing bad is going to happen. But if the altitude is never displayed on the screen, that's a really big issue, right? So what we do when we're concerned with safety is we create a small focus specification of problems that we think could happen, really bad issues that we want to avoid. We come up with a way for the software to avoid those. We then simulate these situations and see if the software does work correctly given these hazardous situations, right? So this is much more possible to prove than full correctness because it's a much more limited set of factors that we're looking at. And ideally, what we can then do is prove that the software does avoid these particular hazards. And if proofs are not possible, we can still, like reliability, gather evidence, gather observations, but just make sure we're looking at these specific situations. So if we're ignoring all the other elements of correctness, the safety specification is often a lot easier to analyze than our full specification. And by looking and thinking about hazards in isolation, it's a good brainstorming exercise. We can better think through what kind of situations could be really catastrophic for our system and how we avoid those. So correctness, reliability, and safety, all three of those are contingent on a set of planned operating conditions. We have an environment we know the system is going to operate in. We can plan for that environment. We can plan for the functionality of the system. Those all define a form of normal. What is the normal operating environment? What kind of conditions do we expect? And all specifications we write make assumptions, whether those are implicit or explicit assumptions. But what happens if all of your assumptions are being violated? What happens if we land outside of the specification altogether? And that's where robustness comes in. If we have software that's otherwise correct, bad things can still happen if our assumptions are violated. So in those situations, we're not psychic, like I said, we can't really plan for them. But how the system fails when this does happen really does matter. If there's no hard drive space left suddenly, it might not be reasonable to expect file changes to save. If someone's driven off with our ATM, we can't really expect money to be dispensed, right? And those kind of issues. So software that's correct might still fail. But if in those situations, the software can gracefully fail, if we can prevent users from being harmed, then that's a robust system, right? Robustness isn't really something that's provable or really demonstratable in a meaningful way, but it's something that you aim for in your design of your software. So when you're designing software to be robust, you accept failures can happen, and you try and control how the system fails in those situations, designing it to counteract some of these issues and gracefully degrade their services. Basically, rather than letting your ATM dispense money, it should display an error message if it suddenly loses a network connection, if it can't sense whether there's money in the system. So this is more of a design principle, but it's something to think about when you're building your system. You can't really prove that the system is robust, but you can try and put as many guardrails in place so that if bad things happen, they're less likely to affect the users. Now, ideally, we have all four of these. And if you have software that's provably correct, well, then it is also reliable, right? But the reverse isn't necessarily true. If the system is reliable, it might still not be correct. You haven't proved that. You've just watched it for a while. So you think it's probably pretty good. You did a pretty good job of showing reliability, but catastrophic failures can still occur, maybe under rare circumstances. Now, software that's safe is, maybe, or sorry, software that is robust might not be safe at the same time, right? It can try and counteract bad situations, but again, catastrophic failures might still happen, right? And software can be correct but not safe. You might have an inadequate requirements document. You might not have really looked at these different hazards that can occur, right? And software can be safe but not correct because it's good with regard to the hazards, but there's still problems outside of that area, maybe more minor issues. Those can still occur. So these don't always come together. You can have some subset of these and not all four of them, and rarely you have all four. More often you aim for reliability and maybe a bit of safety and robustness, and correctness you hope for, but you don't really prove. All right. Any questions so far? Everyone still with me? All right. Now, testing is there to reveal faults so that they can be identified and removed. And identifying and removing faults is always a useful goal. But finding every fault is nearly impossible in any complex system, right? It's definitely not cost effective. We can always test more. But we need to stop at some point. We need to release a product at some point. And to do that, what we need to do is we need to establish some criteria for when we're done, when we can claim to be dependable enough. So correctness is not really a good basis to aim for. What we more often aim for is that reliability, right? Robustness and safety, they're also nice, they're important, but they're also, again, hard to measure. They're not necessarily the best grounds to base your release on. You could be safe, but the rest of your software could still be an annoying mess, right? It could put out the wrong output and crash and do very minor issues, even if it doesn't do anything horrifically bad. So it doesn't show dependability either under normal circumstances. So when we talk about dependability, reliability is the best basis for establishing how dependable your software is and when you can release. Reliability can be measured, it can be demonstrated, and it can reflect both normal and these rare, abnormal, hazardous sort of situations, right? So next we'll talk about how you measure reliability. But first, there is a question in the chat. What exactly is meant by a catastrophic failure, right? So a failure that completely brings down a system or something that harms a user. Okay, so catastrophic, basically, I would say is anything that carries some kind of legal, financial, or human risk is really where I'd put it. There's not a single hard line here, but anything that carries something beyond just annoying the user, right? So completely bringing down a system could be a catastrophic failure, especially if it leads to side effects. So if the whole system goes down and it's up again in 30 seconds, maybe that's not quite catastrophic. But if you're losing financial transactions, if you're losing data, it also can be. So I'd say anything that carries some sort of a financial risk, a security risk, a legal risk, or some kind of harm, like physical harm to a user. Those are all things that are is what I would put under a hazard or a catastrophic failure. Any other questions so far? All right. So let's then talk about reliability and availability and how we measure these, right? So I know we've already talked a little about what reliability is, but if we want to start putting a definition on it, when we talk about reliability, it's the probability of a failure-free operation for a specified time in a specified environment for a given purpose. Now that sounds really vague, doesn't it? There's a lot of qualifiers: specified time, specified environment, given purpose, right? And what I'm actually getting at here is that reliability can be different for different people, different users of your system, this type of system you're building. Each of those has different requirements for how much is reliability is enough, and what does reliability look like from the user perspective. So informally, reliability is really a measurement of how well users think the system provides the services they require. So how well they think it provides the services. Reliability is something you improve when you remove faults in the most frequently used parts of the software, right? So for testing the system, we want to go out and find and fix as many faults as we can. But when you do, there's going to be some kind of improvement in reliability. How big that improvement is really depends on how often that fault affects people. Some faults are rarer to encounter than others. So removing X% of the faults lying in your code doesn't mean you get a corresponding X% improvement in reliability, right? So, I mean, it might be you went and removed 60% of the faults you found, and that only gives you a 3% reliability improvement because people didn't really see those very often, right? Reliability depends on how users work with your system, and not all users will see a particular failure occur, right? Different users access different functions, or they have different security settings. They use the system in different operating environments, or at different times of day, different interaction sequences, and so on, right? So when you're measuring reliability, you want to think a little bit about your context, all those different qualifications. When are you observing the system? What situations are you observing it under? What kind of users are you modeling and trying to emulate when you run these test cases, right? So you want to establish some different operating scenarios, different profiles of the user types you think will interact with your system and the actions they're going to take so that you can measure reliability under these different contexts and track how it changes over time. Now, fundamentally, though, reliability is something that can be measured, unlike correctness, unlike robustness or safety. We can set conditions and we can measure reliability in these different scenarios. So once you define reliability, it's something you can measure and you can argue for. It can be divided into levels, and you can specify a level of required reliability for release. And this tends to start in your system requirements. So from the non-functional requirements side, you can define, well, the number of failures that are allowed, for instance, or the time in which the system is allowed to be unavailable for use. You can define thresholds and measures, right, that you use to assess reliability. And in your functional requirements too, you can define how the software avoids failure, how it detects a failure and recovers if it does happen, how it corrects for failures to keep operating, right? So your non-functional requirements can define how we judge reliability, and your functional requirements can determine what the system does to be more reliable. We can check those requirements and make sure they're being met, and we can set measurements. We can establish release thresholds, right? So that's why reliability is great. So that said, how do we measure reliability? Honestly, measuring reliability is actually quite traditional and normal when you're building hardware. But it's actually a little more complex for software. A lot of hardware metrics aren't really suitable for software. Because from the hardware side, you're looking at component failures. You're looking at need to repair and fix hardware, right? So if the hardware has failed, if a beam collapses in your building, you get people out of the building and you don't let them back in until it's been fixed, right? Software isn't quite so binary. I mean, pun intended, right? In software, failure can be more easily recovered from, or a system might still be operating even when failures have occurred. Failures might be partial. And the thing is, with hardware, your design is assumed to be correct. The problem is your implementation. You just had a component wear out or something go bad, right? And you swap it out and try and fix it. In software, parts don't fail. There's no hardware degradation. When you have a software failure, it's really more often a failure of your design, an issue in your code or in your higher level architecture and your requirements. But I mean, even in the code, it's a design failure. The system's often still available. You can restart it. Partial failures are a very normal thing. So when we talk about measuring software reliability, we're considering factors like how often it fails, what is its uptime, how long of a time period do you have between failures, more than just is it working or not. Now, one measurement that did originate from hardware, but still is a good starting point for talking about how you measure software reliability is its availability. So availability is essentially asking, as a measurement, is asking whether the software can carry out a task when it's needed. It's both a way to measure your reliability, it's a measurement of it. It's also a specific quality attribute of its own that's often examined. So as part of reliability, it's a measurement of how often the system is running over a period of usage, right? So over the past 24 hours, how often was the system up and taking requests? It shows that the system under normal circumstances can generally be counted on to deliver its services. Now, as a standalone quality attribute, it's referring to the ability of the system when something bad happens to mask or repair issues so that the service outage period doesn't exceed a certain value over a time interval. So if something bad happens, how do we recover from it quickly? Right. So from this perspective, as a quality attribute, it's saying, well, when a failure occurs, can the system recover from it? It's important to remember the difference here. So when we look at reliability, we're looking at whether the system is working or not. Is the system able to deliver the correct results? When we look at it, availability as a quality attribute, we're looking at specifically at scenarios where something bad happened and it has to now recover or avoid going down, and what should it do in those scenarios? Right. So as a measurement of reliability, availability is the uptime divided by the total period of observation. It gives us a pretty clear indicator of when the system is able to respond. Now, this is important, but not perfect on its own because it doesn't really take into account incorrect computations, right? If the system gives you the wrong answer, it's still operating. That doesn't affect its availability. So it's not really going to be reflected there. Here, we're just looking at, well, how often is the system down and not responding? If the system doesn't crash, doesn't affect the availability. You also want to be very careful when you read availability figures because one decimal point makes a huge difference, right? If our reliability is 0.9, that means it's down for 144 minutes a day. That's actually pretty terrible. 0.99 though goes down to 14 minutes. 0.999 down to 84 seconds, 0.9999 down to 8 seconds, right? So that decimal, the number of places after the decimal point really does matter here for when you're specifying your availability. Now, as a standalone quality attribute, as I said, availability is the system's ability to avoid or recover from failures. Now, when you have failures, failures can be accounted for in different ways. We can try and prevent them in the first place. If they do happen, we can try and work around them and tolerate them to the extent possible, or we can try and recover when there is a problem. One of the most demanding tasks in building a high availability, fault tolerant sort of system is to understand what kind of failures can arise during operation. And once those are understood, you can put strategies and actions and code in place to account for them, right? So faults can be tolerated, recovered from, or prevented, and as you build your system in that way, it becomes a little more resilient to faults. As we might care about how faults are detected, how frequently failures are allowed to occur, what happens when failures happen, how long the system is allowed to be down, uh, when these faults and failures can occur safely, how they can be prevented, and what kind of notifications are needed when a failure occurs. Those are all things that you need to plan for as part of ensuring availability. Now, because a system failure is observable by its users, the time it takes to repair from that failure is the time until that failure is no longer observable to the user, that they can resume using the system as normal. That can just be a brief delay in the response time. It also might be the time it takes someone to fly out to a server farm, flip a key, restart a system, which can be a lot longer, right? So the notion of observability, observing a failure occurring, it can be a tricky one. For example, the Stuxnet virus was used to affect nuclear reactors, and it was unobserved for months as it very slowly corrupted the system and did damage. Is the system available during that time? Technically not, because bad things are happening, but people didn't really notice it. So it means the notion of availability is a little bit tricky to define sometimes. Also, unlike hardware, we are often concerned in software with the level of capability that remains when the failure has occurred, this degraded operating mode. To what extent is the system working correctly, even if it has to work around some problems, right? Now, a second measurement is what's called the probability of failure on demand, or the POFOD. This is the likelihood that if you make your request, it results in a failure. So it's defined as the number of failures divided by the number of requests made, right? So if we have a POFOD of 0.001 and we made 1,000 requests, that would mean that one of those 1,000 failed. This is useful in situations where a failure is serious. So this is measured independently of how often we make requests, which is something you might also consider. But here, what we just care about is the number of requests we made, not the period of time, not how often requests are made. We just care about the total number of those that failed. So this is very useful in situations where failures are serious and they are independent of how often these requests are made. So maybe if you're monitoring like a chemical reactor, for instance, you might want to, and it shuts down the reaction if it's overheating. You might want to measure your reliability using the POFOD because requests are probably going to be infrequent. You over the entire lifetime of the system, we might only do this 1,000 times, right? But any failure of that request would result in bad consequences. So, one of 1,000 requests failing is not great if you're Amazon. But if it's over the entire lifetime of the system, maybe that's more acceptable. Now, the flip side of this is a third measurement, which is the rate of occurrence of faults, or the ROCOF. Now, this one we consider the time period instead of the number of requests. This is looking at how often failures are occurring. So what we do is we measure the number of failures that occurred over the period of observation, right? So, a ROCOF of 0.02 we've had 2 failures per every 100, whatever a unit of time is, right? Minutes, seconds, days. You define a unit of time and you measure the number of failures that occurred over that time. So very often that's, what we'll do is we'll allow n failures over however many hours, seconds, minutes, days, months, and so on. This is a very appropriate measure for systems that have requests being made on a very frequent basis. So I mentioned Amazon a second ago. There you might have 1 million transactions a day. So rather than looking at the number of transactions that fail, you might be looking at the time period. So you care, okay, over a day, how many of those 1 million transactions do we allow to fail? All right, so for ROCOF, for ROCOF, we don't care about the volume of requests. What we care about is the number of failures over the time period. For the previous one, the POFOD, there we don't care about the time period, but we care about the volume of requests. All right. Now, one more that we might consider include the mean time between failures. This is the average time that elapses between observed failures. Here, we only care about the time that the system is up and operating. So what we do is get the timestamp of every failure, the timestamp of when the system resumed service, and then we check for the average amount of time before it goes down again. So this is a bit separate from availability, where we specify a limit on how long it's allowed to be down when it fails. Here, we're looking at how often it can crash and cause downtime. This is important in situations where the time in operation is super important. So if a user has a long session with a piece of software, if you're working, for instance, with a CAD system, you're designing blueprints, an architect might spend an entire day on their design. And when they save their work, it needs to do some rendering. It might take a lot of storage space. So you might not save incredibly often. It'll interrupt your work briefly. So you want, in that case, a mean time between failures that's very high, right? Because what you want is it to be longer than the average session time. You want it to be unlikely they lose their work, basically, right? Before they save and they do that rendering process, especially if you can't constantly consume the resources to save or do this work regularly or save partial results, right? So then you try and observe that or try and ensure there's a long time between these issues. Right. Are there any more questions right this second? All right. So why don't then we take let's just take a 10-minute break. It's 10:55, so at 11:05 we'll resume and continue this. And in the meantime, feel free to send any questions in the chat. All right, we can get back into it. There's been some interesting discussion going on in the chat, so maybe take a peek at that too if you're curious. Talking about reliability. But let's go ahead and get started again. So as a reminder, here are the 4 reliability metrics we've talked about. The availability, which is our uptime over the period of observation. Our probability of failure on demand, which is the number of failures divided by the number of requests that were made. The rate of occurrence of faults, which is the number of failures divided by the total time that's elapsed over that period. And the mean time between failures, which is our average time between the observed failures. So now I'm going to make us do a little bit of math, right? So we have a Mentimeter here, and I'm going to switch over to that. So can everyone see the Mentimeter slide? So right now what we've got is a piece of software with 10,000 requests have been made. And when we made those 10,000 requests, we had the wrong results in 35. In 5 cases, it crashed, right? And then in those 35 cases, we got the wrong answer. So total 40 failures. So what is our probability of failure on demand? So yeah, 40 divided by 10,000. Anyone else? Right. So I mean, everyone gets the basic point, right? There were 40 failures that occurred, right? So yeah, many of you are good here. So 40 failures, 40 divided by 10,000, right? So a couple of you are off by on your decimal points a little bit, but um but I mean, yeah, generally the answer is right here, right? So 40 out of 10,000 failed. So great, let's then go to the next one. If I can find my mouse, there we go. Right. So now we've got a different situation. We've run the software for 24 hours. Over that period, we made 6 million requests. So there were 6 failures. So what is our ROCOF and what is our probability of failure on demand? So it looks like people are thinking a little bit. Our probability of failure and demand is probably our simplest, right? That was just the same thing we had previously. 6 failures, 6 million requests, right? You don't need to calculate, it's like 10 to the negative, 6, right? So some sort of incredibly small number. A rate of occurrence of faults, so, right, that can be, we have 6 failures over 1 day, depending on how we want to measure this. 6 over 20 over or if we want per hour, what we might want said is 0.25 per hour, right? Because we had 6 over the whole day, or we could just say 6 per day, depending on how we want to measure this. But again, you get the idea. I'm just trying to make you think a little bit. All right, here's another one. We've had 1 week of observation. There are 972 requests over the week. It failed 64 times. So what is our rate of occurrence of faults? And right, of those are 37 crashes, 27 were incorrect computations. Yep, so Yeah. This again, we're looking at our period of time, right? Now, if we want to look at this, yeah. Yep, good. All right, so people get the idea here. Right. So we might have some targets we want to hit. We might want to be hitting availability greater than 99%, a probability of failure and demand of less than 0.1, a Rokoff of 0.3 per hour. So we might want to do a bit of manipulation of our units here. But you get the rough idea here of what we're aiming for, right? So for, our target is a Rokoff of less than 0.3 per hour and probability of failure of less than 0.1. Well, we have this data we can use, and we might need to manipulate our units a little bit. But we're trying to get it into the right comparison for our requirements. So Rokoff, what we have at a basic level of 64 failures, trying to throw you off a little bit with the crashes versus incorrect output, but all of those matter for the Rokoff. So 64 failures over a period of observation. We want to get that in the point by hours. So it's 0.38 per hour, which means we're actually violating our requirements. We're not quite hitting that. Right. Our probability of failure and demand, that's 64 over the number of requests, 972. Now our availability, we're aiming for that greater than or equal to 99%. So what we know then is that it's got an average of 2 minutes to restart after every failure. So what we can do is we can use that. Well, what we're really looking for is restarts. So we're looking at crashes. This is where that crashes versus incorrect output distinction matters, right? So there are 64 failures, but only 37 of those result in downtime. When it's down for 2 minutes. So what we know is it's been down for 74 minutes over that period of time. Now that period of time, we said that it was a week. A week, we can get that in the minutes. That's 10,089 minutes, which means we have a 99.3% availability. We were down for 74 of the 10,000, roughly 10,000 minutes. That's a pretty good availability. So that does meet our threshold, right? So is the product ready to ship? Well, what we saw in the last slide was that rate of occurrence of faults wasn't quite what we were hoping for. It's still a little high, but otherwise the product is looking pretty good. So some minor improvements in reliability would be sufficient. Are there any questions on the measurement aspect? You guys sort of get the idea. I, made you do a little bit of math here, but seems okay. All right. Everyone good? Looks like there's one question here. So someone's asking about SLAs. So service level agreements, I believe, and availability is usually part of those. You define some kind of availability requirements, right? So I mean, there you'll see things like 5 nines is a common statement, or 6 nines is pretty common too, and that's 0.99999% reliability or availability. There's also a question, both Rokoff and POFOD take crashes and incorrect output. That's correct. So those two are useful for software because they take into account all failures of the software, whether it crashed or whether it continued to operate. Whereas availability really only cares about these crashes that occurred, like the things that actually take the system down and put it out of use entirely. Any other questions right now? Okay. Now, raising reliability is quite expensive. Sometimes it is actually cheaper to accept that the system is unreliable and just pay for the results of the situations, right? You might not get 100% reliability in the end. It's just not cost effective. So you aim for reaching a certain acceptable threshold. Everything beyond that, that's allowed to happen. So basically, it's a bit of an optimization problem. How do we balance reliability improvement versus minimizing liability? We should always aim to improve reliability. We should do as much as we can, but there is a tipping point, and there's a point where it's not worth the money to keep putting effort into this. Now, what you do to raise reliability and at what point you stop, it depends a little bit on the social and political and marketing factors around your system. A reputation for unreliable products might hurt you a lot more than the cost of improving reliability. And if that's the case, making that reputation higher and continue to increase reliability, even if it's expensive, is worth it. It also depends on what happens when the system is going to fail, right? So we've had a little bit of discussion already about severity of failure, about risks, about harm to users. All of those need to factor into when the improvements you make to reliability. If there's health risks, if there's something where a car might crash, that requires a high level of reliability. But maybe minor issues can be tolerated. And then this also factors into which faults you prioritize fixing. Common annoying faults are going to lead to a large increase in your perceived reliability, and so those might be important to fix. But that said, even if severe faults are rarer, you still probably want to fix those first because of the risks of when something does go wrong. But how often the failure occurs and its severity both factor into your prioritization, and they factor into what level of reliability you set before deciding this is good enough and we need to release. All right. So now let's talk about some of these other quality attributes. So next we'll talk about performance and scalability. So performance is all about time. It's about the ability of your software to meet its timing requirements. So when an event occurs, if there's an input, a request to the system, if a message arrives, if a certain timing threshold is met, the system has to respond to those events, and it needs to do so in a reasonable period of time. There's a question, is there a way to factor in system stress and availability? Right, so Rokoff and Pofod could drastically change depending on load. So this is really why you often consider several different measurements at once. System stress can factor into your availability because you might see increased uptime as stress increases, but it's not necessarily clean to see that, but you will see a change in your availability. Similarly, those other measurements could change depending on the concurrent loads. So all of those can this fits into, we talked about the having different user profiles earlier. Similarly, you might have different load profiles and different conditions that you measure reliability under, because all of those are dependent on the current operating conditions. You might also do things like simulating different network speeds and different system configurations. So all of those also affect when you measure reliability. All right, so back to performance then. Characterizing the kind of events that can occur and how the system responds to those and how long it takes to respond is really the essence of discussing performance, right? So when you look at systems, you might get input in the form of requests from users, and that might be tens of users, that might be tens of millions of users. If you're looking at the control system for your car's engine, events come from the operator's controls, but also the passage of time, and the system has to control. In the traditional combustion engine, you've got to control like when you fire the ignition, and similarly, even in electric cars, there's certain events that have to occur at particular time windows, right? As well as events coming in from the control of the car itself. For a web-based system, your desired response might be the number of transactions you can process in a minute. For your engine control system, it might be the allowed variation in the time that events occur. But in any of these cases, what you want to do is capture some kind of pattern. When do events arrive? What form do those events take? And what kind of response should occur when those events occur in terms of the time it takes to deliver that response per user. But in any case, performance has always been a driving factor in how we design systems. It's frequently compromised the achievement of every other quality. Often we prioritize performance over almost anything else in our software. And all systems have performance requirements, even if they're not written down, we still have expectations. Your word processor might not have explicit performance requirements, but if you wait an hour for a typed character to appear on your screen, that's too long, right? So there's still performance requirements. So performance is a fundamentally important quality attribute for all software. Now, when we care about performance, there's a lot of different ways we can measure it. And often you're going to employ more than one of these at once. But we might care about, for instance, the latency. So between the arrival of the input and the issuing of output, how much time occurred. We might care, though, also about the variation in that latency. So we call it the response jitter. If we perform an action 10 times, what kind of variation was there in the performance over those 10 times? We might care about the throughput. So how many transactions can we process over a period of time? And especially as we get more and more users, we might care about that total number of requests we're processing across the full user base versus the latency for any one individual user. We might care about processing deadlines. So what are the points where we absolutely have to have completed a particular computation? And we might even care about how many events the system failed to respond to because it was too busy to respond. So first of all, latency is one of the most common ways that we assess performance. That is our length of time it takes for any one particular interaction with the system to complete, right? So, I mean, if it's a person sitting at a computer, that might be the length of time between them clicking a button on the screen and then that response appearing on the screen, right? For a database, that might be the time between invoking the service and sending a request versus the database returning the data you asked for, right? So you send a query and you get the data back. When we look at latency, there's a couple of aspects we look at. There's first of all the responsiveness, so how quickly the system responds to a routine workload, like a user request. So the response time for an operation is usually on the order of a few seconds, right? The key consideration for these workloads is keeping up user productivity, ensuring the system doesn't slow down its users unnecessarily when they're completing tasks, right? So that can take into account the responsiveness of the user's device itself. So how long it takes for like a mouse click or a keyboard press to be recognized, or the responsiveness of the software itself, how long it takes you to acknowledge and respond to that request when it comes. But both of those affect the total perception of how long it takes for the software to be used, right? Now, you might also care about the turnaround time it takes to complete larger tasks. So maybe not a standard workload, but a larger, less common, but still the worst case response time, basically, right? And this might not be seconds, this might be more minutes or hours. And there, whether we're considering more where the task can be completed at all in the time available to it, and the impact that task has on the rest of the system while it continues to run. So this is more of our rarer but more severe, more worst case situations. It might be important to consider how quickly partial results in those situations can be reproduced as part of the long running task. We might provide summaries or information on at different intervals and where we stand with processing this workload, right? And that might include looking at, well, if we have a daily throughput of 850,000 requests, this process should take less than 4 hours in total. Or it must be possible to resynchronize and reset within a certain period of time if something bad happens. But we might want to consider, as I said, the responsiveness, that's more of your average scenario, normal job, how long does it take? And then we might care about the time also for these larger tasks and your worst case scenarios. We also care about the variation in the response time. Response time is something that's always non-deterministic. Computers just don't always take the same amount of time to return a response. That can be that some machines are slower than others. It could just depend on what other processes are running and using resources on your machine. But if you run a task several times, it's not always going to take an identical amount of time to finish. Now, if this is controlled, that's great, right? If you have if you have some sort of limitation on how much variation there is. So if it always takes between 9 and 11 seconds, that's great. That's fine. That's not really a problem. But if sometimes it takes 10 minutes instead of 10 seconds, that is a problem, even if it's relatively rare, right? So what you want to do is have some kind of idea of how much variation there can be and place some constraints in how much variation is allowed. If it ever violates those windows, then that could be a problem. So rather than saying that a particular task should take 10 seconds, you might actually put a window around this saying, well, it'll take between 9 and 11 seconds. That's okay, right? And if those boundaries are violated, then quality might be compromised. We also might care about the throughput, so the amount of workload the system is capable of handling over a particular period of time. So the response time is for a single user, the throughput is for all people using the system concurrently. Both of those are very important, especially as the number of users increases. And throughput and response time have a fairly complex interrelationship. In general, the shorter the processing time for a single request, the higher the throughput. That's how you hope the relationship looks. However, as the concurrent load increases, the throughput is going to rise at the same time, but the response time for an individual transaction tends to increase a bit as more people use the system at once, placing more demand on the resources of that system. So you might see a relationship where if you have 10 users, each request takes 2 seconds, but when you get to 100 users instead, 10 times that number, each request starts to take a little bit more time individually, which will in turn affect the throughput you see on your system. And if you prioritize throughput, that can come at a cost to your response time. It's quite possible to be in a situation where your throughput goals can be met only at the expense of some response time. And then you care about all of those 100 users having a reasonable experience, even if each one of those users takes a little bit longer than they would if you had fewer users, right? It might be that, with 10 users, each of those can perform 20 requests per minute, and that's a throughput of 200 per minute. Whereas when you get up to 100 users, each of those takes longer. They can perform 12 per minute, but that's still a very high throughput. That's still very nice. That's at 1200 per minute then. That's still quite a reasonable throughput, even if each individual user takes a little longer. So as an engineer, you need to make sure that your stakeholders and you understand that those kind of interrelationships and where your priorities are. Do you care about handling more users at once, or prioritizing the experience for each user you do have, but maybe placing a limit on how many you can support with your resources? Now, in some systems, so there's a question, does throughput define the capability, or is it the hard limit in the amount of requests? It's more looking at your capability, I would say. What you might really your available resources is more of your hard limit, and what you might do is try and define your resources to meet a certain throughput threshold. So then with event deadlines, some systems have very strict timing constraints. Last class I held up the pacemaker, right? That little medical device. So some very strict timing windows where they're allowed to shock your heart. So sometimes what you really care about are these deadlines, these points where you must have completed a task. There's a little bit of variation allowed in the response time, but once you hit a certain time point, you have to have finished. I talked to a couple minutes ago about an engine controller in your car. So in a combustion engine, the fuel has to ignite when the cylinder is in this position. So that places a deadline and when the fuel has to ignite. And a lot of other systems have similar requirements. If those times are missed, your system is going to fail. And so these deadlines put these boundaries on event completion. If the system is busy, it might ignore input, it might queue it until it's too late to matter, but we need to meet these sort of windows. But you might also track then how many input events are ignored and try and limit the number of those because the system was too slow to respond in time for that deadline. All right, everyone's still good? Any questions so far? All right. And that leads into scalability. So scalability is a separate quality attribute, but it's very highly linked to performance. That it's really almost a subset of performance. Scalability is the ability of your system to um, basically to scale the performance based on the resources available to the number of users requesting those resources. So as you add more resources, a scalable system is able to deliver fast response time to each user. And as you remove resources, it should still be able to deliver its services in a reasonable manner, but maybe a manner that's slightly degraded to the user base requesting them. But it's the ability of the system to handle adequately the requests that are coming in and to make effective use of its resources. Now, as I said, performance and scalability are highly linked. Increasing your system's capacity for work, giving it more requests, or sorry, giving it more resources, generally then means you should be able to process an increasing number of requests and maintaining the speed for each of them. Two kinds of scalability we care about are horizontal scalability, which refers to adding more resources to your set of logical units. So adding another server to your cluster of servers, for instance. This is in a cloud environment. This is your elasticity, right? It's enabling you to add or remove machines from a resource pool. Vertical scalability or scaling up, on the other hand, is for each of those units giving more resources to them. So that might be adding more memory to each individual computational unit you have. So horizontal scalability is adding more computational units. Vertical scalability is adding more resources to each of those individual units. So the problem that arises with either type of scaling is how to effectively utilize additional resources when you add them, or how to make effective use of lower resources when you lose them. Being effective means that if you add additional resources, that should result in some measurable improvement of some of system quality, generally your performance. So if you add resources, you should see a performance improvement. Or it could mean that it didn't add undue effort to add resources or change your resources, that it didn't disrupt your operations to add or remove resources. So technically, scalability is making your system easy to change in a particular way related to can you easily change the amount of resources you have without drastically affecting the system's ability to operate. Now, the problem with achieving scalability by adding hardware is that it usually isn't very effective unless the system is designed from the start to take advantage of new hardware, right? So if you design your software to be a single threaded process, adding more CPUs doesn't necessarily help you. And increasing the speed of that single CPU it's running on, even that might be of limited help. But if you design your system with concurrency in mind, where you have many different individual running processes, then having more CPUs makes it easier to scale and improve your performance. If you can't partition your workload into many cooperating processes, you won't be able to take advantage of adding more units to run those processes on, right? So you want to design your system to scale. Now, to assess scalability, what you're really looking at is still the same measurements you use to assess performance. Right? Addressing more requests is often part of your performance assessment. And so when we design scenarios to assess scalability, what we do is we design performance scenarios where we have an idea of what happened before, what was our earlier performance. Earlier, we could process requests in 15 seconds. Then we define an addition to scalability. And now that we've added scalability, what should happen now? Well, previously it was 15 seconds. Now it should be running in 10 seconds, right? So assessing scalability uses the same measurements as performance, but what we look at is the change as a result of adding these resources. Response time, throughput, response jitter, and so on. When we assess scalability, we're directly looking at what happens when we add resources and what happens when we remove resources. And what we're looking at in terms of our measurements of the response then is what was the change. Now we might also look at this in terms of availability. So one aspect of scalability is when we change resources, does this disrupt our operations? Does this disrupt the running system? So we might also be looking at a change in availability as a result of increasing or decreasing, and often you're looking at decreasing the resources available. And we might say, well, if we decrease the resources, then the availability should still remain at 99.9999% or whatever, right? We might also look a little bit at the distribution of load between these resources. So are we effectively making use of the resource pool? Are we distributing an even percentage of requests to each server that's up and running? Right. So those are all aspects we might look at, but most often this is the performance change or the availability change as we increase or decrease available resources. This makes sense. Are there any other questions right now? All right. So one more quality attribute we want to look at then is the security of the system. And this is not a security class. We're not going to go into a huge amount of detail, but it's something that you do very often want to consider to some extent as part of your testing as well. So security then more formally is a measurement of our system's ability to protect its data, its information, and its services from unauthorized access, while simultaneously still providing access and providing that information and data to the people or the systems that are supposed to be using it, that are authorized. Right? It's basically the question of, are we able to protect our software from malicious use, from attacks? An attack is any action that you've taken against the system with the intention of doing harm. And that can take a number of different forms. That might be an unauthorized attempt to access data or services that you're not supposed to be using or accessing, or it might be an attempt to go in and modify that data, right? So retrieving data, modifying data, and with the intention of corrupting the system in some form. Or it could be an attempt to deny services to legitimate users. So it may not be that you're trying to get into the system and change anything, but it might be that you're trying to prevent the users who are supposed to be there from using the system and cause the system to crash in some form. So we define security then as the processes and technologies and policies that let the owners of the resources of that system control who can access which resources. Right. So when we talk about these actors, people working with the system, that might be humans, but that might also be other pieces of software that interact with the system. Right. We might have resources then that we're trying to protect. That's parts of the system that are considered sensitive. That might be data. That might be operations of and functionality of the system that we're trying to protect. Right. And so access to the resources is something that we want to protect. And we want to keep an eye on the operations that the actors in the system want to legitimately perform on data in the system. They might have a legitimate interest in reading information, changing information, executing processes, and so on. But those actions should be limited to those who are supposed to be using the system. So when we are focused on security, we're looking at defining policies that define what legitimate access to resources is and which actors are allowed to perform those actions and what mechanisms are in place to ensure that only legitimate actors can use those resources, right? This is often very specific to the system you're building. Your security concerns for a web service are very different from the security concerns for your nuclear reactor, but still most systems have some kind of notion of who is supposed to be accessing it and what actions should be taken to limit access to those outside of that set. Right, but in any of these cases, security is basically how you allow the right level of access to the right resources, to the right actors, while preventing anyone from outside of that set from using the system. Now, the simplest approach to characterizing security is three aspects to it, what we call the CIA, the confidentiality, integrity, and availability. So first, Confidentiality is the property that data or services are protected from unauthorized access. Right? So, for example, a hacker can't go and get your tax return on a government computer. Integrity is the notion that data and services are not subject to unauthorized manipulation. So your grade hasn't been changed since I assigned it to you, for instance. And availability, as we talked about already, is that the system is up and running for legitimate use. So a denial of service attack won't prevent you from ordering a book from the shopping website. So characteristics used to support confidentiality, integrity, and availability include authentication, that we can verify the identity of the parties that are responsible and involved in using a process of your system. You know, if you get a message from the bank, can we ensure that it actually comes from that bank? Non-repudiation is the guarantee that the sender of a message can't deny that they've sent it, and the recipient can't deny having received a message. Right? So if an action occurred, the parties involved shouldn't be able to deny their involvement in that process. If you ordered a book from Amazon, for instance, right? They can't deny that you ordered it. They can't deny that they sent it. You can't deny having received it either. An authorization is the granting of to a user of the privilege to perform a task, right? And the notion that only authorized people should be able to perform that task. So a banking system authorized legitimate users to access their account and no one else. So those in general are how you characterize your scenarios for security. What forms of authentication took place? How do you ensure non-repudiation? How do you ensure proper authorization? Right. So question of how can non-repudiation be verified and enforced? So that might be mechanisms in place to notify that an action has taken place successfully. So code to detect that the action took place and note that in a form that can't be modified. But generally some kind of mechanism in your software that records that this action was completed. I mean, you see this a lot in messaging apps, right? Where you have separate like check marks for the message has been sent to the server, delivered to the user, and then the user has seen it. So if we're trying to achieve security, that can be characterized as approaches that try to detect an attack, that notice an attack has taken place. That could be that you've tried to resist an attack after detecting it. So in some cases, it's sufficient just to detect it. In some cases, you go beyond detection to resistance. Other cases of reacting to an attack. So an attack has taken place, we failed to stop it. Now, how do we react? How do we try and stop it if it's still actively taking place? Or how do we limit the extent of the damage if an attack has taken place? And also what we do to recover from an attack after it's taken place. If it has happened, if some damage has been done, what do we do to get back to a normal operating state and notify users that there's been a problem? We also care about what is being protected, and that can be data being stored in your system. So that's what we call our data at rest. It could be data being transmitted between parties. So if we're sending data somewhere, we might try and encrypt and protect that data in some form. Or it could be running computational processes that can be attacked, right? So we might have a service up and running that can internet accessible, and we try and prevent it from going down when there's a denial of service attack. Now, it's important here to recognize that security is not this simple binary property. You're not secure or not secure. It's not really a binary state. It's more of an active process of risk management, especially because security is something that's constantly evolving. There's constantly new attack vectors, new areas to protect from, new technologies that may be secure or insecure to various degrees. But really, it's important to recognize that at some point, all systems will be compromised in some form. If you might be protected for a very long time by being not famous, by anonymity, but eventually most systems are compromised in some way, especially because we've grown increasingly better at automating attacks, right, and attacking at scale. So really then security is trying to avoid attacks to the extent possible, but when they do occur, trying to quickly stop them, prevent damage from occurring, and recover and getting back into service quickly. Right? What you're trying to do constantly is balance your level of risk against the cost of guarding against risk. And those costs come in a lot of forms. I mean, it might be that you need to make constant updates to your code to prevent a new attack from occurring. It might be that you need to have redundant servers to quickly recover from a denial of service attack. It might be the legal cost of data being compromised, but there's a lot of different costs to consider, and you're trying to balance this risk of a problem occurring against the cost of preventing that problem from being bad, right? And it's important to set realistic expectations then in the minds of yourself and your stakeholders for your system and make trade-offs then that address the real security risks you're facing and acknowledging that those costs are going to change over time as your company grows more successful. The risks of security issues are going to grow much higher versus your brand new developers writing your first app, then maybe there's not going to be a major issue. Now, security then is a measure of your system's ability to protect its data, protect its services, right? Any attack then is an attempt to break confidentiality, break integrity, to break or break availability. And the response to an attack is to try and preserve those qualities or to deter attackers by monitoring their activities. So you don't really measure security in one universal way. What you're trying to do generally is assess how well the system is responding to an attack or to demonstrate how well a policy is working, right? So your stimuli when you're assessing security is some kind of attack, one particular form of attacking your system, and you look at how the system reacts in that situation. All right, your responses include things like auditing the attack, detecting the attack, logging what happened during the attack, reporting the attack, analyzing the attack to try and identify the extent of the damage. This means there's not really a universal metric for how you measure security. So there's a question: what is the meaning of transferring the risk, right? So I got this graphic from elsewhere, so I'm gonna think for 2 seconds, right? It might be that we have someone else who takes on the risk for us. Now, that might be that if you are hosting a system on the web, for instance, you're not necessarily providing your own cloud infrastructure. A lot of the risk actually is being managed by like Microsoft or Amazon or Google, whoever your cloud provider is. They're handling a lot of the security policies as well. So that's actually a transfer of risk from yourself to a third party. I guess that would actually be one of the primary examples of transferring risk is when you're working with third parties to provide some of your services. And there you are somehow dividing the risk management with them. Some elements are still up to you and your software, right? And if a problem occurs, some of the blame will fall on you if you're not adequately guarding. But some of the security management is also in the cloud provider side, things like firewall management, you're not doing yourself. All right. So as I was saying, there's no universal measurement for how we measure security, right? What you're generally doing when you're looking at security is looking at specific attack vectors, specifying how the system responds to those particular types of attacks, and then having some kind of measurement of how well you did to based on what that policy is, like how you're addressing the attack. So if your goal is to avoid an attack altogether, particular attack altogether, what you might measure is, was that attack avoided or not? How often? That might be looking more at some of your reliability measurements. Did the system crash when this attack occurred? If your goal is to recover from a denial of service attack to limit the downtime, you're looking at things like your availability measurements. If your goal is to identify the attacker, then you might be more looking at a yes or no. Was the attacker successfully identified or not? You might be looking at the percentage of the data that was protected or whether the data was protected at all from an attack. If you're trying to stop an attack, you might look at the time it took to stop that action from occurring and what happened during that period, right? But generally, you're looking at the kind of attack that you're assessing and then coming up with an appropriate measurement to detect to keep track of, well, whenever we ran those attack vectors, what happened? Were we able to successfully detect, stop, prevent damage from those attacks? Does it make sense? Any questions? All right. So that was a lot. Hopefully then this sinks in a little bit. Um, but to wrap up a little bit, this lecture, what we looked at was five of these quality attributes: dependability, performance, dependability, availability, performance, scalability, and security. These are some of the primary ones that we care about for most modern systems. There's a lot of others that we might care about as well, but those are really some of the five most important. And really for this class, dependability is the big thing, right? How dependable is our software? Is it able to correctly deliver the results we expect? This is broken down into four sub-attributes: correctness, reliability, safety, and robustness, with reliability being chief among those because we can't generally prove correctness, but we can observe the system over time and track its reliability. Now, with the reliability, that depends on who is using the system, what are the functions they're interacting with, and when. So you need some kind of expectations on different usage patterns for different kinds of users. And then for those different profiles, we can measure reliability using these measurements of availability, of the rate of occurrence of faults, the probability of failure on demand, the mean time between failures. Now, in addition, availability is the ability of the system to recover from failures or mitigate failures. Performance is how fast the system delivers its services in terms of either individual users or throughput for all users. Scalability is the ability of the system to respond adequately to the amount of resources available to it. So the change in performance as we either decrease or increase resources. And security is the ability of the system to protect its data and services from unauthorized access while still working and providing access for the people who are supposed to be using the system. Right? Security isn't necessarily measured. There's not a single level of security, but what you do is provide attack specific measurements. Right. So there's a question, is there any difference between the security or safety? So yeah, so safety is a little bit different. The safety of the system is its ability to avoid having bad consequences in particular defined scenarios. That can include security, but it's a little broader. It might just be that if the network went down, is the system able to continue operating? That has nothing to do with its security. There's not an attack going on, but it's still avoiding a bad situation. So that's that broader umbrella of safety. Right. Any other questions? Then that's all I've got for you today. There is no exercise session this week in case you missed that last time. So there's nothing tomorrow. The next lecture is next Monday. And there we're going to look at scenarios and defining how you define scenarios for these five different quality attributes of reliability, availability, performance, scalability, and security. If you haven't yet, work on forming your teams. We have this assignment 0 on Canvas that sets out some of the team expectations, and continue to send me. A lot of you have done this already, but many of you still have not formed your team. So keep working on that and trying to do that pretty soon. If you just want to be assigned to in a team, you can also send me an email or note that in the assignment 0 in Canvas, and I'll also put you in a team then too. All right. Any other questions for today? Okay. Then thanks for coming, and we'll see you in person next Monday. Assignment 0 is individual. Someone asked about that. But as part of this, send one email per group to me with the group members.